Hello, and thank you for joining us for this webinar this afternoon. I'm just going to wait another minute or so just for a few more people to join in. I'll be back in just a minute. Hello, and thank you for joining us here for this webinar today on dust hazard assessment and basic testing to see what your basis of safety is going to be. So my name is Samuel Ayres. I'm the Business Development Manager for Sigma-HSE. I've been in the business for just over 2 years, and I'll work out of the UK. So the course objectives, what are we going to be studying today? So basically we'll be looking at how the flammability assessment of your materials helps you determine what your basis of safety is going to be given a unit operation. We're going to be defining the testing protocols for determining dust, fire and explosion risks during unit operations, how to establish safety parameters, and looking at the powder and dust ignition sensitivity and the ignition sources associated with operational equipment, and the factors that affecting ignition sensitivity, explosion severity, and the self-heating characteristics of powders. So Sigma-HSE, where's our areas of expertise? We bring together a global collaboration of companies providing our clients with process safety services and appropriate engineering solutions. We undertake laboratory testing to global customers, to ISO, ASTM, BSI and VDI international standards. Our consultancy services, we cover process safety management implementation, industrial fire and explosion hazards, whether that's a dust hazard assessment, ATEX for our European customers, or DESIR for our customers in the UK. We undertake electrostatic hazard assessments, hazard studies, process hazard analysis, functional safety such as cylinder assessments, and bespoke training workshops, which can be done on site or remotely. Laboratory testing, this is we focus on the powder and fire explosion properties, gas and vapor properties, electrostatic properties of your materials, and chemical reaction hazards. This is such as calorimetry, ARC, ARSST, Keres tube, and DSC testing to help you determine your, the pressure release from exothermic reactions and onset temperatures. And we also conduct regulatory testing. So what is a DHA, or a dust hazard assessment? It's required by the NFPA 652 standard, and it helps you determine the relative hazards of the dusts and powders that are present at site. It's a systematic review to identify and evaluate the potential of fire, flash fire, and explosion hazards associated within your process, whether it's one or multiple combustible materials. Helps you identify the hazard for each process at your facility and components, as well as pinpointing the safe operating ranges and proper safeguards. It provides practical advice for combustible particle solids management and documentation of all your results in the DHA. This webinar will focus on the different flammability assessment tests associated with your DHA in order to make sure that your DHA is suitable for your unit operation. So obviously this webinar will be talking about the testing with regards to explosive materials, flammable materials. So what happens when things don't go too well? So as many as you're aware, the Imperial Sugar disaster, over 30 died, unfortunately, due to an explosion, secondary explosion due to sugar buildup. And more recently, the Tuas explosion, everyone may not be aware of this one. It happened in Singapore this year. This was an explosion in a mixer due to powdered potato starch was the cause of this one, unfortunately. So, the conditions for a dust explosion? First off, the dust or powders, using a site must be flammable, combustible, and airborne to form a cloud. The concentration of the dust must be within explosible limits. Particle size distribution should be capable of propagating a flame. And the atmosphere, there should be enough oxygen to support the combustion. There also must be a sufficiently energetic energy source to ignite it. So I do apologize if that was too loud for anyone. So there we go, the fire triangle. It's basically the fire triangle with mixing and confinement added in to cause an explosion. So the fuel and air must be intimately mixed and in a confined environment. So how can testing help you determine your basis of safety? Basis of safety, there could be 3 ways to determine it. There could be explosion prevention, to stop an explosion ever happening, the avoidance of ignition sources, and as a last resort, explosion protection. So ideally, you'd like to stop the explosion happening. If you can't stop the fuel being there, you need to make sure you don't ignite it. But if you can't rule out all the ignition sources, then you must protect it to stop it propagating anywhere else and keeping it contained. So we're going to look into now the testing of your dust and powders which are associated with the explosion prevention part of the basis of safety. So first of all, it's removing the fuel. This isn't always possible in most operations. You may have flammable powders and dusts, and getting rid of them just isn't going to happen. But for gases and vapors, you can work outside the flammable ranges. You can work below the LEL, which is the lower explosible limit, or above the upper explosible limit. You can remove the oxidant, so there's no by nitrogen purging or argon purging. But that requires some further data to help you achieve that, which we're going to go into shortly. You could remove all the ignition sources to stop an explosion happening, but sometimes this isn't feasible. There's always ignition sources, especially static or hot surfaces, which you can't always mitigate. Process control. But again, this isn't always reliable. So first of all, what tests can we do to determine whether your material is flammable? It's called the go, no-go screening test. It's also known as a Group AB or dust combustibility test. So this is a picture of our piece of our equipment. It's called a 20-litre sphere. So this test will help us determine whether your dust is flammable or not. We will use 10 kilojoule igniters, and in that pressurized container, we'll create a vacuum and we'll ignite we'll try to ignite the dust. If they go, then obviously we know that the powder is explosive, but that's pretty much all the data we have at this stage. There is further testing that you need to go on to help you with your DHA. If it's not combustible, then that's great. You've not got this isn't a combustible dust, and you can use it as such. So we briefly talked about the explosion prevention limiting oxygen concentration test. As everyone knows, oxygen is required to create a fire and therefore create an explosion. If you removed all the oxygen and there is a completely inert atmosphere, again, that would help you. But that's expensive, having a constant purging. What about if we, reducing the oxygen level only a certain amount by the help of purging, but it's reducing it to a certain level that there's not enough oxygen to create a flame. So this test, what we'll do in that 20-litre sphere is we slowly decrease the amount of oxygen until we can find that sweet spot where there's just not enough oxygen there to help for the explosion not to happen. So if we look at on the right hand side, say sulfur, you only need to inert to a level of 7% oxygen, and for it to be safe and not be in an explosible range. So in the long run, testing to determine how low you need to go in your oxygen will help you instead of just blanket inerting. And this test is conducted to ASTM standards. Again, another test is the concentration test. This basically determines what concentration of dust is required to achieve the explosion. So working below that, which is sometimes known as the lower flammable limit, will help you not achieve an explosion, again, conducted to ASTM standards. So those three tests there, the go, no go test, the LOC, and the MEC, those three tests can help you use explosion prevention as your basis of safety, providing it's A, not a flammable substance, or B, you're working outside its flammable range, whether that's by its concentration or by the oxygen level there to help, by adjusting the oxygen level to make it into a safe zone. The next stage, which was part 2, is the avoidance of ignition sources as your basis of safety. But for that to be effective, you need to know how sensitive your dusts are to different sources of ignition to be able to make sure that you're working outside the sensitive range. So we'll highlight some of the sources of ignition which are the potential of, I'm not going to say common because not all of them are, but the ones that are out there that could ignite, big enough to ignite your fuel. So hot surface, that's a key one. It's hard to always not have those in the workplace. Flame, smoking, hot work, again, is a difficult one to always avoid. Static electricity, this is a present threat and it can be hard to mitigate at times. Electrical apparatus, mechanical friction and thermite sparks, lightning, not all of them are overly common, but exothermic reactions and spontaneous combustion. This is one that doesn't get too much attention, but it is something to definitely consider, especially if you're doing a lot of bulk reactions, any sort of calorimetry work. Ultrasonic waves, ADO compression and shock waves, stray electric currents within installations, ionizing radiation. Again, we go a bit further down the risk. I've highlighted the ones in yellow of the 7 which are most likely to be present in your workplace at one time. So this is probably one of the most common tests that is done probably throughout the world to help people determine how sensitive their dust is to electrostatic sparking. So this is the minimum energy test. What will happen is the fuel will go in the bottom of this tube. It's lofted up under pressure, goes for a spark by those 2 electrodes that are nearly joining in the middle of the tube, and we'll basically see what happens. We'll start at a high energy, so a very 1,000 millijoules, and work our way down if we keep seeing a flame. And we'll work down to the lowest where we start seeing a flame, so we can determine what the value is of what is a sufficient energy source. There's two tests we do in this tube. There's the capacitive discharge, which is electrostatic sparks, and the inductive discharge, which is mechanical sparking. This is trying to simulate metal on metal, metal sparking in a blender, for example, if one of the bearings goes off. So they usually do come back at slightly different values. That's why doing both tests, especially if you're doing mixing or blending, is recommended. But pretty much all the time, the electrostatic test is always done on the material. I do have a video of this one shortly. I did check it. It was working before I started this presentation. So bear with me. I would advise maybe just turning sound down a little bit, because some of these videos can be a little loud. So, yep, I'll just go across to it now. Yep, it is going to work. We'll try and turn it down on my end as well. Okay, here we go. So this is our tube. So that's a simulator. That's what we're trying to achieve. We're trying to achieve that to determine what level of energy is going to do that. So some different materials can go at a really low energy and be really dangerous. I think I've got a table next to show you some key materials or what sort of energy level is suitable to ignite them. So cocoa, that's quite high, 100 to 300 millijoules. GRP dust, 30 to 500. But sugar, that's a very key one, 10 to 30 millijoules. A human can sometimes, when you touch a piece of metal and there's a bit of static, that can sometimes be between 30 and 40 millijoules. So that can potentially ignite anything below, say 30 millijoules, so aluminium, APIs in the pharmaceutical industry. So that's the MIE test. Basically, in a nutshell, it's trying electrostatic sparking, what level of spark is going to ignite your dust. The next test is the minimum ignition temperature test. This is in the Hartmann furnace, as seen here. This is trying to determine what level of what temperature is going to ignite your dust when they're dispersed in a cloud and they're going to come across a hot surface. It's sometimes known as the auto ignition temperature, but we generally refer to it as the MIT, which is the minimum ignition temperature. I do have a video for this one as well. But yeah, we start with a range of 2 to 700 degrees Celsius. So what we'll do is we'll start at a high temperature and then work our way down to see where the onset is of when it becomes flammable. And for this test, we will use, to give you a safety factor, it's always 2/3 of the value that we achieve. So if we see a flame at 300 and we don't see a flame at 295, then we'll give you the figure of 300 degrees Celsius as the onset, but the safety factor would always be 2/3 of that. So it would be 200 degrees Celsius is your safe zone. And that's what we would advise you when you're selecting equipment, that it would always be 2/3 of the MIT value. I will add though that this temperature does coincide with the next test I'll be talking about, so I will refer back to equipment selection in a second. But I've got a video of this test as well. So sorry if that was loud, I do apologize. I'll just play that again. So what's happened? Again, the fuel powder was inserted in here under pressure from just air. It was pushed through the furnace and obviously ignited. So moving on to the test that always coincides with the minimum ignition temperature test. This is called the layer ignition temperature test. Basically a hot plate, we use a 5 ml layer of your fuel, your powder, dust, and we try to see when it starts to flame or when it starts to smoke or smolder. What we would do with this one is very similar. Start at high temperature, start at low temperature, but this one we start at low temperature, work our way up, and find out when it starts to work, or when we start seeing a flame. And we would use whatever this, say this is 300 degrees again, but we don't use 2/3 of this value. We use whatever the value was minus 75 degrees C. So this would be 225 would be your safety factor. So for example, to help you choose, help you with item selection, if you had an MIT of 300 and an LIT of 300 when the onset was, you would use the MIT's value of 200 safety factor being 2/3 as the true safety factor, because it's obviously lower than the 225 LIT. You would just use whatever one was the lowest. And that's why these two tests are always done in conjunction, because they do usually come back with different figures. So you just use the lowest. And again, these are conducted to ASTM standards. So that ends the ignition sensitivity. Oh, we do have a video. Just going to turn this one down again. Bear with me a second. So yeah, this is we're just trying to determine what temperature this sort of thing happens, or if it bursts into flames. That a lot of different materials do different things. Some just glow, some smoke, some they do go into flames. And this is what we're looking for to help you determine your equipment selection. So that was explosion prevention and the avoidance of ignition sources, and what tests help you determine if your basis of safety is going to be suitable. The last one is explosion prevention. So this is these are the tests which are going to help you determine what containment systems are going to be suitable, what LEV systems will be, what size blast panels or blast vents or pressure relief valves you're going to need. So I'll just put all these up and I'll talk through them separately. So this is again the 20-litre sphere. This is the same piece of equipment that we do the go-no-go minimum ignition concentration and limited oxygen concentration testing, but we just use it slightly differently this time. So this is the aim of this test is to determine how much pressure, the maximum pressure that is detected when the explosion happens, and the rate and the calculated maximum pressure rise, so dP over dt. How quickly is that pressure generated? We'll do this test at multiple times, varying the concentration of the dust and looking for its worst case scenario. So with this data, it will help you determine those explosion protection items, as I previously mentioned. So at the end of this, you'll get given like it's called the dust class, HSE class. It's ST0, 1, 2, or 3. So I'll just go across to the next slide. So ST0, there was just no explosion. There was no pressure was detected. Examples of that is silica, which obviously an inert. And then ST1, 2, and 3 increasing in severity. Please take a note to sugar is an ST1 dust, but obviously from the Imperial Sugar disaster back in 2008, just because it's what is classed as a weak explosion doesn't mean it is not dangerous. But a lot of the APIs and aluminium, magnesium, and those metals, all very strong ST3 plus explosions. So something else which hasn't been considered yet, particle size. The general rule of thumb is the smaller the particle size, greater the surface area. There's that small area for a reaction to take place. But the effect of the particle size can't be calculated in any way of how that's going to affect your tests. Say, for example, you've done a load of tests on a material that was 500 microns, which in terms of particle size, that's quite a big particle. But you actually found out through doing some testing or on the particle size that you're actually using, and it's more like 63 microns or 100 microns. The data that was generated on 500 microns is more than likely going to be very different to what you're actually using. So your basis of safety may not be the right one. So you may need to possibly look at retesting at a more representative sample of what you're actually using on site. But generally speaking, as the surface area increases, so as particle size decreases, the explosions violence, explosion severity increases, but the energy required for the ignition decreases. So it becomes more dangerous, and a lower millijoule spark or a lower temperature would ignite it. So that's why it's extremely important to potentially retest at different particle sizes if you believe you are using different particle sizes in the data you've already got. I hope you can see this graph okay. So down the left is a different variable. So decreasing particle size, decreasing moisture content, that's another one that's not been covered. Atmospheric pressure, increasing temperature, increasing pressure. So these are the generally effects it could have on the tests that we covered. But as you're decreasing particle size, you have a lower MIE, a greater Pmax and KST, and the lower MEC and the lower LOC. And so these are just, I'll leave this on here for just 30 seconds or so you can have a little look. But generally, if you're using things at different temperatures or different particle sizes, maybe worth retesting. Right, so moving on. So that was, in essence, how testing helps you do your basis of safety. But you always got to remember that a basis of safety is you've got to have a primary and secondary source. So if your primary source was the explosion prevention, because you're going to work outside the flammable limits, for example, and then explosion protection, or it could be your secondary basis of safety. So you'd still look to always have a secondary just in case your primary failed. Can you elimination of ignition sources? The basis of safety is not always possible, because sometimes you can't always even identify all the ones that are on site without doing your DHA. So you would need to do DHA to help you identify them. And then can they be overcome? Sometimes, but not always, especially electrostatic and sometimes hot temperatures. So those are the two which can't always easily be overcome, because you may need to be operating at a high temperature for your reaction to be efficient. And again, one important one to remember, normal and abnormal conditions. They both need to be considered. What happens outside the norm? Equipment selection is obviously for hazardous zones, 0, 20, 0, 1 and 2 for your gas and vapors, 20, 21 and 22 for your dusts. And also we talked about temperature class of equipment. So the maximum permissible surface temperature of different equipment is extremely important, especially if you've now got the data from the MIT and LIT tests. So if you've got say an item that's allowed to go up to 300 degrees, that's the maximum permissible, but your safety factor says you need one that goes no higher than 150, then you've got an issue now. So that's something why testing helps you determine whether they are appropriate or not. And sometimes instead of going for one of the more expensive pieces of equipment, which has one of the lowest maximum permissible surface temperatures, if everything that you're using on site has a relatively high MIT and LIT value, that could be quite ineffective to do it that route. So sometimes testing can help you. Mainly testing is there to help you make sure that you've got the right piece of equipment. That's goal one of testing for those two tests. But it also could help you save money. So explosion protection, we've talked about the Kmax and Pmax and KST value. So there's three types generally of explosion protection. There's the containment, there's to vent it, or the suppression either from an inert gas. But all of these measures require proper isolation to stop the flame from explosion from propagating to different areas of the factory. So containment. It must be able to withstand the maximum pressure that is expected and maintain that strength over the lifetime. That's why the 20 litre KST and Pmax test is extremely important. If that can only withstand, a lot less than what you could achieve by the maximum pressure that's detected in the 20 litre, then it's not going to be suitable. And again, it requires the effective isolation from fast closing valves and rotary valves. Relief venting. This is very common. You come across this a lot, whether it's sometimes they're doors, sometimes they're bursting discs, they're panels, or they're pressure relief valves. Again, they have to be suitable, that they will be able to vent enough pressure safely enough. So the panel has to be large enough that it requires effective isolation, and it uses. But again, that's what the 20 litre sphere will help you generate enough data to help you select, or your designer to select the right venting option. Here's some pictures of how not to do it. So on the left and in the middle, you've got two vents, explosion vents, pointing at each other. So that's not exactly going to be ideal if you're going to just have an explosion one and put it through to the other hole, to the other area. And the third one, they've got to be maintained and clean, and make sure they're going to be effective instead of being glooped up with powder and dust on the outside there. Explosion suppression. This is achieved by having a detection system in place, which is going to sense an explosion, sense a flame happening. It would be a CO detector, and instantly it's going to inject a suppression agent, so that'll nitrogen, argon, in quick enough into that area to suppress the flame. These can be quite expensive, and they need to be maintained and tested quite efficiently. And again, but it does require effective isolation as well. So here's a brief little diagram of routes for testing. So can start from the top? Can the material form a flammable atmosphere under a foreseeable condition? If it can't, if you've tested it and it just won't ignite, so you can go down the avoidance of flammable atmosphere route. Again, then is the material flammable? Nope. So avoidance of flammable atmosphere. And how sensitive? You need to determine how sensitive, how severe the explosion could be, and what are those flammable limits. And those are the tests down the left-hand side that help you determine those questions in the middle. And then down the right-hand side, it goes you what route you should follow if that is going to be the base of safety that you're going to choose. So why choose Sigma-HSE for testing? We have global laboratories. We're able to achieve turnaround time of 5 to 7 days from receiving the sample. Our technicians from around the globe have decades of experience. We're ISO accredited, that's ISO 17025. And now we currently have over clients in over 30 countries, including USA and Canada. So I'd like to thank you all for joining us. And if anyone has any questions regarding any sort of consultancy or testing that we've covered today, please do not hesitate to get in touch with us at the bottom there, or alternatively via India or via the UK. I wish everyone to stay safe out there, and thanks again for joining us. Take care.